Welcome back to The Explainer. Today, we're diving into something really fascinating. We're looking at a cutting-edge challenge in computer science. How on earth do we shrink these massive AI models down to a manageable size without losing their incredible reasoning capabilities? We're going to break down some seriously groundbreaking research on making artificial intelligence more efficient, accessible, and ultimately more powerful.
Okay, let's dive right into this. The central problem we're facing today is that modern AI models have become, well, absolute giants. They require massive compute costs, huge amounts of memory, and vast energy resources just to run. If we ever want these powerful models running locally on our phones or our laptops, we desperately need efficient ways to compress them. But how exactly do you shrink a trillion-parameter brain without turning it into a complete amnesiac? That is literally the billion-dollar question in AI hardware right now. So, here is our roadmap for this explainer. First, shrinking giant AI models. Second, pruning the student architecture. Third, healing the teacher model. Fourth, the unified transfer pipeline. And finally, measuring what actually matters.
Let's start with part 1. Shrinking giant AI models, the bottleneck of modern AI.
To understand where we're going, we first have to understand why the old brute force ways of compressing models just aren't cutting it anymore. Think of a neural network like a massive, overgrown tree. The old paradigm, which is called unstructured pruning, is basically like going through that tree and individually plucking off specific leaves. You're just zeroing out individual weights, and sure, the tree is technically lighter, but the overall shape, it's exactly the same, which means modern hardware doesn't actually run it much faster. The new paradigm, structured pruning, is more like taking a saw and cutting off entire branches. We're talking about removing whole channels, heads, or layers. This approach maps beautifully to dense inference kernels, giving us those universal hardware speedups we're really after.
Moving on to part 2, pruning the student architecture, discovering the hidden network.
Now this is where we shift our perspective from just randomly deleting weights to something much more profound. The researchers call this architecture pruning. It's the process of deriving a compact student model by pruning at the structural level, so layers, channels, heads, rather than only masking out individual weights. The crucial paradigm shift here is that this is no longer just about sparsification. We are actually trying to discover a highly efficient, streamlined student model hidden inside that massive teacher model. We're using the big model to tell us exactly what shape the smaller model should take.
Now, what's really interesting about this is how incredibly practical it has become. Methods like sheared llama or Minitron are proving that by pruning down to a target shape and doing a focused recovery training, you can get incredibly strong small models. Take sheared llama, for example. They reported recovering a strong model using roughly 3%, just 3% of the compute it would have taken to pre-train that same size model from scratch. That's a huge win.
But we definitely have to be careful here. While shrinking the width of the network or removing attention heads is generally a pretty safe path for compression, aggressive depth pruning, meaning removing entire layers, is super dangerous. The research explicitly warns that stripping out too many layers can cause the model's performance to abruptly collapse, like just fall right off a cliff. That's exactly why depth ablations are such a critical diagnostic tool when we're performing any kind of model compression.
Part 3. Healing the teacher model, from genius to great tutor.
To really get this next part, think of a classroom. A brilliant, massive teacher model, an absolute genius in its field, isn't always very good at explaining things to a beginner, right? So we introduced this concept of teacher healing. This is any method that explicitly improves a teacher model's distillability, or the quality of its supervision, before it tries to transfer knowledge to a student. The big takeaway here is that a teacher's quality shouldn't just be defined by its raw top-line accuracy or how smart it is, but by its transferability. Basically, how well it can actually pass that knowledge on.
So how do we actually heal a teacher? Well, the research gathers a few scattered techniques. You can calibrate its predictions so the teacher isn't overly confident. You can force it to provide step-by-step rationales or explanations. You can even MSE train it, have it revise erroneous labels, or purify conflicting advice when you have multiple teachers. All of these steps work together to transform an unapproachable superbrain professor into an empathetic, calibrated tutor that a smaller student can actually learn from.
Which brings us to part 4, the unified transfer pipeline, the ultimate compression recipe.
The taxonomy proposed in the research brilliantly maps out the entire landscape we've been talking about. On one side, you've got the structural changes, your depth pruning, width pruning, and that defines the physical shape of our new student. On the other side, you have the teacher-side refinement, things like calibration and rationale enrichment, which ensures effective learning. What this does is link architectural pruning together with teacher healing into one unified ecosystem. So the crucial point is this three-step recipe. Step 1, discover the best student architecture by structurally pruning the giant model. Step 2, heal the teacher model to improve the quality of the signals it sends. And step 3, distill the knowledge from that healed teacher directly into your newly pruned student. Right now, this represents the absolute most compute-saving, effective way to shrink massive AI models.
The ultimate takeaway here is pretty straightforward. If a massive teacher model already exists, you really shouldn't waste your time training a smaller model from scratch. The absolute best performance for your compute budget, what researchers call the best expected Pareto point, comes from combining an architecture-pruned student with a healed teacher knowledge distillation recovery. It's just the smartest way to do it.
Of course, putting all this into practice requires a huge effort. The paper proposes an intense 18-week experimental timeline. It really highlights how rigorous factor testing, where you independently vary the student architectures and the teacher signals, leads to these kinds of breakthroughs. It's a highly methodical process. You're essentially testing different pruning pipelines against various teacher healing modules to find that absolutely perfect balance.
And finally, part 5. Measuring what actually matters, beyond top-line accuracy.
In this final evaluation stage, we have to completely rethink how we measure success. And this brilliantly illustrates the paper's 3 core claims, tying our whole narrative together. Claim 1, architecture pruning is the right abstraction for hardware. Claim 2, teacher quality equals transferability, not just accuracy. And claim 3, when we evaluate a smaller model, we have to measure what is preserved and what is lost during that transfer. Because think about it, a smaller model is only useful to us if we can guarantee it hasn't lost critical off-metric properties during the shrinking process. We can't just look at headline accuracy scores and call it a day. We have to measure calibration, robustness, uncertainty awareness, and reasoning reliability. Did making the model smaller compromise its safety, or its ability to simply say, hey, I don't know? These off-metrics are what truly determine if a compressed model is actually ready for the real world.
Which leaves us with this final vital question. As AI models inevitably continue to grow to trillions and trillions of parameters, absorbing vast amounts of data and compute, is the future of AI really just about building bigger and bigger brains? Or, as this research so elegantly suggests, is the real frontier actually about building better teachers to pass that knowledge down? Thanks for joining me for this explainer. Keep learning, and I'll catch you next time.